Okay, so having talked about fields generally, let's start to look specifically at gravitational fields. So there are two key figures that got us to where we are with gravitational fields. One was Kepler, 1571 to 1630, and the other was Newton, 1643 to 1727. So you can see that Kepler was a long time before Newton really, was really in a position to do very much with what Kepler said. So Newton was 13 when Kepler died. So those are our two key figures. And what did they contribute? Well, Kepler had three laws. He had the law of orbits, the law of areas, and the law of periods. And this one is the one that's most important, and the derivation of this we're going to do in a little bit. So that's important, you need to know that. So three laws of periods. He said that the square of the period of rotation of a planet around the Sun is proportional to the cube of the radius of that rotation. He said that planets orbit the Sun in ellipses. An ellipse is kind of a square circle. Here's one focus, here's another focus. So what he said was the Sun is in one of these foci and the planet orbits in an ellipse around the Sun. And then his law of areas, he said if you drew a line between the planet and the Sun, as the planet orbits, that line would sweep out equal areas. That is to say, it would cover an equal area from, let's say the Sun is here and the planet is here. As the planet goes around the Sun, the line connecting them would sweep out an equal area in an equal period of time. So those are his three laws. So what did Newton do? Well, Newton took Kepler's laws and he said that planets are moving basically in circles. They might be a little bit elliptical, but they're basically in circles with constant speed, and this is circular motion. He then extrapolated from the fact that the Earth attracts objects near the surface, that is to say, if you drop something, it falls, to say that planets, moons, and the Sun all attract each other. That's quite a step if you think about it. To see in the classic picture, you have Newton sitting under an apple tree, the apple falls, and he goes, whoa, gravity. Well, that's one thing, but to say, and therefore, because the apple is attracted to the ground, the Earth is attracted to the Sun, that's quite a step, but that's what he did. And then he said that this attraction between the Sun and the planets and the moons and so on, this is the source of the centripetal force. And finally, he guessed that the force of attraction is proportional to the mass and inversely proportional to the square of the radius of the orbit. So that's quite clever too. So then what did he do? Well, there's your mathematical expression. He said that the force of attraction, the centripetal force, is proportional to the mass of the planet, inversely proportional to the square of the radius of the orbit. So the centripetal force, the force of attraction, is equal to some constant times the mass over the square of the radius. That makes sense. Now, let's take the Sun and some orbiting planet. They're moving in circular motion. We know that the period is 2 pi over omega, so omega is 2 pi over t. You've seen all this before with circular motion. The centripetal force we know is mr omega squared, which if we stick our omega in and squared, we get mr 4 pi squared over t squared. Now he said this is the centripetal force. And this is the force causing the circular motion. So this mr 4 pi squared over t squared equals km over r squared. If we rearrange that, then we get r cubed times some constant equals t squared. So r cubed proportional to t squared, that's what Kepler said. So here's the significance of that. Newton, using his own ideas, has come up with the same relationship as Kepler's law. That's a pretty good start to your theory of gravitation. So, Newton's universal law of gravitation. He said that any two objects will attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centres. Most of the time we'll consider point masses, and so we won't worry too much about that. But just occasionally you're going to be looking at spheres, and it's from the centre of one sphere to the centre of the other. The centres of mass is the distance that we're talking about. And when we're talking about circular motion around the Earth, we are talking about the radius of the orbit being from the centre of the Earth. You'll probably remember that. So, for objects of masses m1 and m2, a distance r apart, all these quantities are in standard international units, then the force, according to Newton, is proportional to the product of the masses and inversely proportional to the square of the distance between their centres. That is to say, F is some constant, g, times the product of the masses m1, m2 over r squared. That should be a squared. My apologies for that. So, let me just do that. Okay. So that's an important relationship, and G is 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. Now you can get those units by rearranging the equation and making G the subject. You've got F in newtons times R in meters squared, so there's newtons meters squared divided by kilograms squared, newtons meter squared per kilogram squared. This is a very small number. But then if you think about it, if you take 1 kilogram, 1 meter away from 1 kilogram, you wouldn't expect the gravitational force of attraction between those two to be very big. So you'd expect the constant of proportionality to be quite small, and so it is. So that's sensible. Now, when we come to electric fields, the constant there is going to be 9 times 10 to the 9, which is, give or take, 10 to the 20 times bigger. So there's one of the contrasts between gravitational and electric fields. The size of the force between unit charges and unit masses, the same distance apart, very, very different. So, this is a relationship that you need to be able to apply. You need to appreciate the significance of this value. You don't have to remember it, it's given to you on the data sheet. but you do need to understand the significance of it. Notice that this is an inverse square law. That is to say, if I double the value of r, I will quarter the value of f. If I have the value of r, I will multiply f by 4. This is an inverse square law. Okay? That's the same for electric fields. So there's a similarity. They're both inverse square laws. That derivation, if I take you back to the derivation that we did of r cubed proportional to t squared, you need to know that. So this bit we did here, where we said, well, we have Newton's idea that the force is proportional to the masses and inversely proportional to the square of the distance between them. And that this was a centripetal force. We then equated that to our expression for the centripetal force, putting omega in. So we get mr4 pi squared over t squared equals km over r squared. The m's will cancel, of course. And then we end up where we did a moment ago with the idea that r cubed is proportional to t squared, which was Kepler's law. So you need to be able to do that derivation. So make sure that you have that clear in your notes.